Now, remember, roughly speaking, we want to fix our bases so that they are in complex coordinates. They are diagonal. So I could do that simply by looking for some fixed from delta XZ, delta HC bar, bar. But it's actually a little bit convenient for now, not for the first few minutes, not to go to complex coordinates yet, but just to work in general coordinates.
Is it?
No, it's not. Okay. So, start again. So I want to describe the gauge fixing of the diffeomorphism invariance on the worksheet. We want to put the metric in complex coordinates, so that in complex coordinates is essentially the z bar. This means in complex coordinates to set hzz and hz bar to 0, which I can do with these delta functions. But if you want to work in general coordinates, which is also convenient in order to figure out how to parameterize the different possible complex structures on the surface, it's better to just pick some reference metric. Some familiar reference metrics parameterized by whatever parameters I cannot get rid of by diffeomorphisms. I mean, denote them just as some P's. Okay, we'll be more specific about their nature later. And say, okay, I want H to be the same as this up to an rescaling, a wire scaling. So a way I can impose that is that I can pick some auxiliary fields with a property that H tilde, that their trace with respect to the reference metric is 0. Okay. And then put a gauge fixing for the form so it should be clear that this is going to kill all the parts of the metric which are not proportional to this reference metric. Okay. And then I can just build the rest of my ghost action as we did last week. So it still is going to be some reference metric. So by using diffeomorphisms, there is a theorem that we can make, we can always write, we can eliminate almost all the degrees of freedom of the metric up to while rescaling, up to just a finite number, which parameterize the complex structure of the surface. So if you want to parameterize the way you glue your surface together by flat metric patches with holomorphic coordinate transformations. So to take into account the fact that we can have this, so it means that every metric can be reduced up to diffeomorphisms to some reference metric, which is characterized by this choice of complex structure. If I don't want to commit myself to a specific way of parameterizing these complex structures yet, I'll just take this family of reference metrics and leave it at that. And okay. So let me also put a let me write it in a way that is actually diffeomorphism invariant. Okay. Now, what sort of B and C ghosts we need to complete this into a nice object, a nice action which has this topological symmetry. So last week we saw that we would add terms that look like BI, DLA, FI, CA, right? So we introduce a ghost for every group symmetry that I want to get rid of, and an anti-ghost for every another ghost for every constraint. So in this case, it means that we're going to introduce some AB constraint this way, which are going to be the partners of this bosonic capital B's. We're going to introduce some CA, actually CA, which are dual to the vector fields which define diffeomorphisms. So the ghost action essentially looks like this. Because when I do a diffeomorphism, this changes by essentially the A, CB. So F prime here, the AFI, is really is sort of the derivative. So you can sort of see that this action is going to be symmetric under some transformation which changes B by capital B. And changes everything else, such as the metric. This way. Mm-hmm.
Can you explain how you came up with these actions? Like, what's the motivation?
It's just I'm just writing down literally the BI, FI plus BI, AFI, CA that I discussed last week. This is literally the same. I think this is right. But you can also check that this action is indeed invariant under this sort of BRST symmetry. Okay. So a nice feature of this action is that it's actually Wall invariant again. So the ghost introduced in the ghost has not spoiled at least classically Wall invariance, and now we'll have to check if it's there quantum mechanically. Mm-hmm. Sorry. No, delta C. Sorry, so actually I call them Q. Sorry. Well, diffeomorphisms, not quite, because diffeomorphisms do not commute. And remember that Q CA is in general supposed to be the structure constant. So in this case, I think this means something. I didn't write it down in my notes, so I'm reconstructing it from memory. Don't fully trust me on this. It's probably something like this. I likely had to. There might be some other terms where the contractions work the other way. It's a coefficient. Let me see, when I do a Lie derivative to vector fields, right? So what do I do? What is the Lie derivative of? I think this is supposed to be the Lie derivative of v1a dA v2 b minus v2a dA v1b. So, and to parse exactly what this means, but yeah, I think it's likely to be this. Yes, thank you, thank you. It should be needed to take care of this for the variation of the square root of g, I think, and of whatever part of the metric is actually hidden inside this covariant derivative. So it's probably a little bit of a cumbersome calculation, but it's a good exercise in general relativity-like calculations. So, okay, I did this just to show essentially that this ghost action can be while invariant. So. It's far from, again, it's not completely obvious. When you do Wild transformation, there are some terms that come out from the covariant derivative, and sometimes they come from square root of h, and they cancel each other if b is actually traceless, which I thought I'd written and I must have erased. Okay. So this is also another exercise. You probably have too many exercises, but time is what it is. So, okay, so now we well done things in sort of the general setup. We can just go study what happens locally. So the first thing I want to understand is to check what is the wild anomaly for the ghosts to finally get that minus 26 that I've been promising you for a week now. So to do that, I want to go on the cylinder. Once I'm on the cylinder, I can just take my flat metric, go in compass coordinates, forget about all this general setup. So in complex coordinates, essentially my ghosts are B, ZZ, CZ, B, Z bar, C, Z bar. This is a conventional way to write them. And once they're written like that, the action becomes, so these are usually denoted just as B, and these are just denoted usually as C. And this is the conjugate variables. So the action is written as B del S bar C dash bar plus complex conjugate. This is the ghost action. Okay. So it's just the thing over there. Written in complex coordinates. Perhaps the only point that deserves still being mentioned here is that so we get rid of the capital B field to impose our gauge fixing condition. So at some, on occasion we will need to figure out what is the BRST transformation of our ghost, but because we got rid of the field capital B, we need to work a little bit harder. You don't need to do much harder. There is essentially a trick, which is the following. In principle, you could replace your e to the I B A B H A B with something like this. But this is just some constant. See, because the capital B field has 0 is Q closed, whenever you have a ghost action, you can add whatever function of B you want to it without changing anything. This is actually used very often in electromagnetism, where people use, essentially this corresponds to not having a delta function, but having a more complicated function of your gauge fixing condition, which still has the property that integrates to 1 along an orbit. It's like this mirrored version of your gauge fixing condition, or an averaging over many different gauge fixing conditions. The only reason this is useful is that now you can replace B's, when you integrate it away, with variation with respect to this eta. Okay? And put in front of everything. Now, what this eta is doing is essentially it's making your HZZ non-zero, equal to eta. So if you turn on an eta ZZ, so essentially your BZZ can be replaced by del over del eta ZZ, which is just a change of the reference metric in which you turn on a little ZZ component. So this is essentially the same as inserting the stress tensor. Okay. So effectively, when we get rid of capital B, the BRST transformation would be amended to something like this. Okay. Which makes a lot of sense. The vanishing of T was the equation of motion for the metric. We got rid of the metric, but we don't want to get rid of the equation of motion for the metric. This is telling you that the equation of motion is actually Q exact, so it holds whenever you do things that are BRST closed. Okay, so is the action. Something else we can get out of the general expression, which is useful, is that we can get the stress tensor, the contribution of the ghosts to the stress tensor. Because the metric enters the ghost action, there will be a contribution to the stress tensor from the ghosts. If I write it in so classically, can be written like this. Okay. So this is it's the same spirit as we wrote the stress tensor for matter as -1/2 the x. Okay. So it's quadratic expression in the ghosts. You see, C behaves more or less like a vector field. B is as a two-component tensor, and T is a two-component tensor. Now, there is something else which is useful to consider. There is the system of ghosts that we've added have a nice symmetry, which is called ghost number. As you see, the action is invariant under the transformation which rotates B in one direction and C in the opposite direction. So the ghost number symmetry. So there is a current. There is a symmetry that rotates B and C in opposite directions, and there is a conserved current associated to this symmetry. And it can be written as simply CB. So this current has properties that are very similar to the current which we wrote for the free bosons. Okay? So this is associated to translations of the free boson. This is associated to rotations of the BC ghosts. But it has a crucial difference from this one. This current is anomalous. So the symmetry, ghost number symmetry, actually has an anomaly. And the ghost number symmetry is not quite conserved. Mm-hmm.
Can you please write the symmetry transformation?
Sure. So the ghost number symmetry sends C to C and B to minus B. Okay. It's a bosonic symmetry, nothing fancy. And the BRST symmetry has charge 1 under this ghost number symmetry. So when I say this is anomalous, means again that the action is invariant under rotation, under this transformation, but the measure is actually not. The measure, the B, the C, has just, it almost goes back to itself, but it goes back to itself up to a phase, up to a scaling, which means that this current is going to be conserved up to some number that depends on your space, on the shape of your space. Much like the trace of the stress tensor was not quite 0, but it was this now, I'm sorry. C is used both to denote the central charge and the C ghost. And I hope it won't be confusing. You know, usually one is the Grassmann even, one the other Grassmann odd. So usually it's pretty easy to figure out which one is talking about. For example, the left-hand side is Grassmann even. The right-hand side is Grassmann even. So that has to be the central charge. And for the ghosts, one can show something similar. That's sort of for the ghost number current that it is not quite 0, but is again proportional to the curvature of your manifold. Which means on the cylinder would be fine. But when we start studying nice worksheets, that would be interesting. Okay, so how do we quantize this ghost system? Everything was pretty much classical until now. I will cut a few corners because we have only a week and a half left almost. Well, 2 weeks, kind of. But I will just do a Fourier expansion. Well, one corner I should not cut. See, what are the equations of motion for the ghosts that come from this action? Well, they're just del bar B equal to 0, del bar C equal to 0. So B and C are holomorphic, classically. So if I expand them in modes, on the cylinder. Quantization will mean essentially proposing some anti-commutational relations for these modes. And the one that follows from this sort of first-order action is very simple. Okay. So, practically speaking, the meaning of this commutational relation is that if I do an equal time anti-commutator, I roughly get a delta function. Okay. So all of this is completely parallel to what we did for the boson, for the free boson. That's why I'm cutting a few corners, but most calculations can be done exactly the same way as we did the free boson calculations. Now, the first tricky point is to pick your vacuum. So when I want to build a Hilbert space for these ghosts, we're going to build it starting from some vacuum building up. There's a little bit of ambiguity. I mean, most modes have either positive or negative energy. So we can pick our vacuum to just kill by the modes that lower the energy, except for B0 and C0. B0 and C0 don't raise or lower the energy. They anti-commute to 1. So that means that actually the vacuum for the system of ghosts is degenerate. There is some ground state. Which, if you want, is killed by all the positive modes, sorry, the negative modes, positive modes of B. Sorry, I hope this is legible. Okay. And then from this one, I can build a second ground state by acting with C0. And vice versa, if you act with B0 on this guy, you go back to the other one. Okay. And then everything else can be built out of these states by acting with modes which raise the energy. Now, although this is the most natural ground state for the system, I mean, it is the ground state for the ghosts on the cylinder, and it's also the state which naturally appears during quantization, meaning that if you start with a before gauge fixing with your theory in some ground state of the matter system, and then you introduce your ghosts will end up sitting in this ground state, actually precisely this ground state. Now, a way to understand a little bit better the reason we have this C0 and B0 there is that the cylinder has diffeomorphisms which simply rotate it or translate it. These diffeomorphisms do not change the metric. Okay, so it means that the gauge fixing on the cylinder did not actually fix completely the diffeomorphisms. We are still left with these extra translations in time, which are actually infinite volumes, so they can get you some trouble. Now, so the existence of these extra diffeomorphisms that have been not being gauge fixed is directly connected to the existence of some zero modes for the ghosts. Now, when you try to define correlation functions on the cylinder, well, you need to somehow get rid of these extra diffeomorphisms, or at least make sure that you understand what effect do they have. So perhaps it's best to go back to the original description of the gauge fixing, right? So I had this integral of some symmetry group over B, or the ghosts. Something like that. Now, suppose that for some reason, I wanted to add some extra. I want to split this gauge fixing to something. Let's say this. Sorry. I suppose that there is some part of the symmetry that I want to sort of gauge fix separately from the rest. Okay, so there was the set of constraints that I want to use explicitly, and there was some other constraint I wanted to add to completely gauge fix the system. So it means I have some other gauge fixing condition. Now, I might decide to just do part of these integrals, just get rid of these conditions a bit by hand. So I could, for example, just do the Grassmann integral over the B tildes. Okay, that will just pull down something like that, an insertion of the C ghost. And then I can, by hand, do the B integral, say, and put a delta function of a tilde. Okay. So sometimes when there is a little mismatch between my gauge fixing conditions and whatever diffeomorphisms I'm actually using, these sort of mismatches can be dealt with by appropriate insertions in your path integral. So if you want to do some gauge fixing by hand afterwards, after you did your BRST quantization, you can add your gauge fixing as long as you're accompanied by an appropriate ghost insertion. Okay. So the reason I mentioned this, unfortunately, so this was one or two things that I was hoping to mention on Friday, and I didn't get a chance to. And I'm sorry that it has to be transplanted inside this lecture this way. So in order to study correlation functions on the cylinder, we need some brass and we need some cats. Okay? So I define some G and G prime there, and there is some other dual states that I can define. And the one is naturally dual to this G is the one that will be killed by the CNs. Okay. But the one that has actually, so the non-zero inner product between the states, the only meaningful non-zero inner product in the states is this one. Okay. So pretty much because you want the thing on the left to be killed by everything which is not killed by, which does not kill the thing on the right, and vice versa. So here you want something that is killed by C0 and C0 bar because they do not kill G. So to do that, I need to put by hand some C0 and C0 bar. Now, in the context of gauge fixing, these are exactly the sort of insertions for these extra diffeomorphisms that translate or rotate the cylinder. I mean, so this by itself is just a statement in the quantization of the theory of ghosts. It has nothing to do with actual gauge fixing. This theory, I quantize it, and this is the only thing that makes sense. But in the context of the gauge fixing, this is intimately connected with the fact that there were some extra diffeomorphisms on the cylinder that had not been gauge fixed. So that your original integral wanted to be an integral over not all diffeomorphisms, but over all diffeomorphisms which act non-trivially on your metric. So you had to really put by hand a delta over your vector fields, over your coordinate transformations, which would kill the constant vector fields. So onto something like delta of constant vector fields. And this delta of constant vector fields is accompanied by the constant C, constant mode of the C ghost. Notice all the equations I write here, I write for the holomorphic parts, and then there are identical equations involving B bar and C bar. Okay. So every time I write something for the C and C and B, there are identical things written down for C bar and B bar. I'm so behind. Okay. Now it turns out that these ground states, although the most natural on the cylinder, are actually not very convenient for a lot of calculations. In particular, they're not invariant under BRST symmetry. So if you act with the BRST generator over these ground states, you don't get 0. To show this, I will have to write down the BRST charge, which is a kind of a long expression, and I don't want to do that. But you see, there is a simple way to understand why. So we want this sort of things to be true, that the variation of B is the stress tensor. So if you want to think analogously to the free boson, we would like to consider some sort of state which is annihilated by all ln's, and we get an equal -1. This was true for the free boson, for example. And because the BRST symmetry relates B's and L's, relates stress tensor and B ghost, we want to, it's natural to consider a state which has a similar property under the action of the B's. So it's natural to define some state 0, which is annihilated by all the B's, including B minus 1. And so this, you can write this this state simply as B minus 1 G. This automatically will be killed by B minus 1. And then this is not going to be killed by C1 anymore. So it's going to be killed by the Cn or n greater than 1. So the standard, so the ground state can be written as C1, 0, well, C1, C1 bar, 0. Okay. So I thought we could do all the calculations we want in terms of these ground states. For future reference, it will be useful to do calculations instead using this as the reference state. Okay. The real reason will be clear only in a lecture or two when we start relating the cylinder calculations to calculations on the plane or on the sphere. But for now, just let's accept the fact that there is a useful state, 0. It's not the ground state. Has a bit more energy than the ground state, but there's a nice feature that is actually killed by the BRST transformations. Okay. Yeah, I'm sorry, it's difficult to give a completely linear path of thought because somehow the whole story is not completely linear. There are different. Some of the choices are made so that things will work later, and it's difficult to. It's not always easy to justify them immediately. Hopefully, by the end, things will be a bit more clear. But for now, this is a reasonable motivation. So for example, when we describe things like normal ordering, it will be with respect to this state. So let's try to define the stress tensor quantum mechanically now. So we'll do the point splitting. Yes?
I'm still thinking about what you said here, that the delta constant vector fields. So when we wrote the metric as that first line in the board, it's because I can always do that up to diffeomorphism.
Yes.
But why choosing that type of, choosing to write a metric like this doesn't fix the whole symmetry that I have under diffeomorphism. Why are this constant vector field still there as a symmetry?
I mean, they're there.
They're always there, right? But if I read my metric in that way, it's like gauge
Yes.
fixing with respect to this diffeomorphism symmetry, right?
Yes.
Why doesn't it fix all
So essentially it means this is not a complete gauge fixing.
Okay.
So there's still a little bit of gauge symmetry left. To get rid of it, we pretty much we can sort of do it by hand. Put by hand a delta function which restricts the integral over all coordinate transformations only to coordinate transformations which, well, I mean, you can do your choice in different ways, but roughly you want coordinate transformations which do not arise from this constant vector field. At least infinitesimal is a well-defined notion. And we really only care about things that are close to our gauge fixing condition anyway. So if I want to do that, I need to introduce an extra delta function. But it says to do it properly has to be accompanied by some ghost insertion. See, in a sense, because I have a slight mismatch between the B's and the C's, if you want. Because the B's were introduced B's only for the gauge fixing for the metric, but the C's are associated to the diffeomorphisms. So there are some C's which are not fixed by changes to the metric. So, okay, so we can give this definition. What happened? No. I don't know what happened to the front blackboard. So we can go through the same motions that we went through in the case of the free boson. And the result is that you can write it as normal ordering, which means the same expression minus the expectation value on the vacuum plus 13 over 12. Yes. This should be compared to the minus 1 over 24 that we found for the free boson. Now, at this stage, of course, it's still not clear why this has to do with the wild anomaly, right? I made a choice of vacuum, which is not even the natural one. So at the moment, it's just a number that happens to be 26 times the one for the free boson. And if you want to really see the anomaly, I need to compute the Virasoro algebra. So I start with this definition. I take my modes. Or better, I start computing things like the commutator between the L's and C's, the commutator between the L's and B's, and then I use them to figure out what is the commutator between the L's and the stress tensor. And finally, I get the commutator between the L's. And the crucial point is that the central charge inside this commutator is minus 26. Mm-hmm.
Would you write there the normal ordering of the two Grassmann variables?
Yes.
You define it in the usual way?
I define it like this.
All right.
So I subtract the expectation value on this vacuum. But essentially I put to the right all the modes which kill this vacuum. Now again, you could ask me why didn't you do it with respect to the G vacuum? But
is there like a sign convention or something? Because this is a commutator.
Sure, sure. So when you bring them across to each other to put them in the order you want, you put minus signs. So, okay, so doing these calculations is possible. With Mathematica, you can do it in 2 minutes. By hand, it's a little bit tedious. But the end point is this. So this shows you that if you want to do bosonic string theory, you need to put together 26 free bosons describing your spacetime and the ghosts. Together give you 0 central charge for your stress tensor and make it so that thing makes sense. For example, Q square equal to 0 only holds if there are 26 bosons. Now, today, yeah, I mean, I've written down the calculation for the. Oh, I think today, rather than trying to go through these steps, which are really not particularly illuminating, I would like to discuss a bit more the properties of this ghost number current. Which disappeared from the board. Over there. Okay. So again, we can define it by point splitting. This way. And then you can start computing things about it. For example, you can compute the expectation value on this vacuum. So you will find that this is the same as the sort of normal order definition minus 3/2. So what does it mean? It means that this state has Gauss number minus 3/2. Has charge minus 3/2 and the rotations which rotate C with charge 1 and B with charge -1. The ground state has Gauss number minus 1/2. And because we get it from here by acting with C1. Notice there are two independent Gauss numbers. One is acting on the C, B, and C, and the other on B bar and C bar. So I'm just referring to the one which acts on C and B. Then if I act with another C to get the other ground state, I get plus 1/2. Okay. So you see that the definition of, at least things make sense, right? There is sort of a symmetry in the definition between the of C, of G and G prime. Similarly, the dual state also has charge minus 1/2, which should help understand why this is what makes sense. See, if this is charge minus 1/2 and this is charge minus 1/2, it's better to have charge 1. Now, so as I mentioned, the Gauss number current is actually conserved in flat space. So as long as you're on the cylinder, you're fine. But things get interesting if there is a bit of curvature. Now, or if you want to get interesting under Weyl transformations. So to see that, it's useful to compare the definition of the current we gave in some coordinate system with the definition of the currents we might give in some other coordinate system. So if I try to use the exact same definition but in different coordinate system, right, I'm going to subtract something slightly different. Because I'm going to subtract something like this. I mean, suppose I have some other coordinate system as tilde of S. Perhaps I should write it like this. So the difference between the things I subtract in one coordinate system and the ones I subtract in another coordinate system is this expression. This expression is finite, but it's not zero. If you take the limit as S prime goes to S, you get a finite answer, which, sorry, my bad. B and C themselves transform in an interesting way when I do coordinate transformations. Because they had, I mean, one had a upper index, the other had two lower indices. So actually under coordinate transformations, you get some rescaling of this and this. So the things I should really compare are not this, but actually this coming from the B transformation, and this coming from the ghost, from the C ghost. So the C ghost transforms like a vector field, so in the opposite way as the current dx that we saw, while B transforms with twice the second power of the factor which you associate to a current, because there's two lower indices. So if you do this limit, you get minus 3/2 the S squared S tilde over the S tilde. So these factors are definitely important in determining what is the final answer. It may ghosts have been different types of objects, then the answer here would have been different. So for example, if instead of having this sort of, instead of being ghosts, right, so instead of being fancy Grassmann objects with bosonic spin like this, it had been more standard things like fermions, just free fermions, then these factors these powers would have been different. Most of the formula would have looked pretty much the same here. The formula would have been the same if B and C's were just fermions, free fermions. But here you would have had something like a 1/2 and a 1/2, and you would have gotten just 0. So if you have free fermions, the current that rotates them is just perfectly well behaved. But when you have these ghosts, which have this sort of peculiar space-time indices, you get these more interesting results. Mm-hmm.
Can you repeat where you find the way that the ghost field transforms? It's just by requiring that your action is invariant under different.
Well, B has to behave like your metric, because you use the metric to gauge fix. I mean, B has to behave like capital B. And also, at the end, because of this relation to the stress tensor, we want it to behave like a stress tensor. So it has the same kind of indices we use for stress tensor. And C has to be similar to vector fields. So actually, right, if you notice, so originally we put the index of C low and the indices of B up. But so what we're calling here CZ is pretty much the same as a Z bar. And so on. But this particular choice, so we raise and lower the indices so that the final action is simple in these complex coordinates. Okay, so starting from this and from this sort of relations, you can keep playing around and you can find what the commutational relation is between L's and J's. The Fourier modes of the ghost current. Okay. So see the current transforms much like the current we found for the boson. Remember, it was commutation ratio was ln am equal to minus m am. But there's an extra term, a central term, a number, which pops out in some of the commutational relations. And because the stress tensor controls how correlation functions change as you change the metric, because of this extra term here, the behavior of the current is going to be somewhat unexpected when you change the metric. So in particular, you can compute something, for example, like this. Sorry, when I put the 0 here, I really meant C0 bar. Sorry. Now, the conservation of the current in sort of holomorphic coordinates is just the statement that del S bar Js is 0. Okay. And as before, in the presence of a stress tensor, this fails at the location of the stress tensor. The derivative of this is going to give me a delta function. So if I use my stress tensor to just make a change in the metric, on the cylinder, I'm going to find a violation of the conservation law, which is roughly 3 times the curvature if you do things properly. And these 3 will be rather important in what follows. So for example, if I work on a sphere, the ghost number current will fail to be conserved by 3, and so on. So it means that if I look at the operators I place on a sphere, I have to have 3 more C's than B's if I want to have something that makes sense and is non-zero, and so on. Okay, so now I think we have accumulated all the tools that we need to do a calculation of almost all the tools. We need to start computing scattering amplitudes of strings. So we have our ghosts, we have our scalar fields, we understand them more or less on a cylinder. So next we have to understand how to have these cylinders come together into a smooth surface, and how to compute the amplitude for that process. Okay.